And we are live. Now we're live. Okay, now we're live. Hi, everyone. I'm Frank.
I'm Becky.
And we're here for ast111x, our second YouTube live event. And we're going to chat for about an hour on some questions and topics and other stuff like that. So why don't we start off by talking a little bit about who we are and what we do. Becky, you want to start?
Okay. I am a grad student at Arizona State University in astrophysics. And I work on a telescope and camera and we're trying to observe extrasolar planet transits, which is just when the planet passes directly in front of its star, and you measure how much the star dims when it goes past. And you can learn a lot about the size of the planet, how close it is. If it's nearby and we have really, really good spectroscopy measurements of the star, we can learn some things about its atmosphere. So it's a pretty simple concept, honestly.
Cool. That's actually the topic of this week's lecture material. So we have a bona fide exoplanet transit expert here. Awesome. Let's see. So my name is Frank, and I'm a professor here at Arizona State University. In contrast to Becky, I make it all up as I go along. I'm a theorist. My specialty is stuff that goes boom in the dark night sky, so things that explode, the fireworks they make and the elements they make and the periodic tables and all that stuff that they make. So that's kind of in a wide view what I do. And I've been teaching this class, planets, for a while. More than 10 years, let's put it that way. So I enjoy this course. It's fun. It's a little different than my usual research endeavor activities. Okay, so why don't we go ahead and answer some of the questions that are on the discussion board. If people want, you can post questions as we go, and we'll try and pick them up as we go along. So we'll answer some questions, then depending on the time, we may cover some news items that are coming up and other stuff associated like that. Becky, you want to pick one and go?
Sure. Okay. Okay, one of the questions was about ion propulsion, just kind of what we think about it. Ion propulsion is used on satellites and missions that we've sent up. It was used first in 1998 with the Deep Space One mission, which was actually kind of cool. It was just sent up to test a bunch of different technologies. Ion propulsion is really cool, but you can't use it within the atmosphere, so you're still going to need to use chemical rockets to get up. You can't have any ionized material around an ion propulsion engine while it's running, otherwise it doesn't work. And its biggest problem is the fact that it takes a long time to get up to speed. Ion propulsion, I'm assuming you know about, it's basically that they take, I'm forgetting the element off the top of my head.
Xenon.
Xenon?
Xenon.
Okay. They ionize it into plasma and use it to shoot it out the back of the spacecraft. And it actually allows things to go a lot faster than chemical rockets can go. It just takes a long time to get there. So a lot of things use it now once they are up in space, but you can't use it to get out of the atmosphere. So, and we don't have something powerful enough to run like one of those big spaceships yet. Just don't have an efficient enough system to carry enough fuel. So I know you've seen like a bunch of science fiction uses it, but for spacecrafts, but we haven't managed to do that yet. So, but it's an interesting possibility. Can't do it yet, but they're still working on it.
Yeah, I think there's like seven. Yeah, there's like 7 or 8 of them right now. Almost all of them use xenon. I think one of them uses caesium. But yeah, they're the acceleration is slow. It's gentle. It's a gentle push. But if you're going for long ways, the gentle push doesn't really matter. You'll get there. So yeah, it's a technology that'll continue to develop, I'm sure, over time. It becomes a viable option for long-term, big distance travels. Okay, I'll take one. Let's see. Question from, could you please further explain orbital resonances and why integer ratios of periods create an extra push that has significant effects on ... Resonance regarding waves and pendulums like oscillations are easy to envision, but a little more clarity on orbital resonances would be helpful. Okay. One way to think about it is that it's waves on a circle. Right, so if you're familiar with the resonance there, then you've got two circles, and in order to get a resonance, an orbital resonance, the planets have to be at the same relative positions at the same time. So it's kind of like a swing when you push somebody, right? So when you push someone, you always want to be at the same location where they are. So when they are on their backswing is when you do the push. You don't push them when they're up on the rise or coming back down. So in order for a resonance to work, their periods have to be in an integer ratio. It's usually small integers, 1 to 2, 4 to 9, something along those lines. And that's how you get, that's why it's an integer, because they both have to be at the same place at the same time. Okay, so they're not real number integers, otherwise it's like pushing the swing off resonance. Okay, so by definition, if it's a resonance, it's got to be on swing, on integer when it goes. I hope that helps. If not, if that's not sufficient, then go ahead and post a reply on that, and I'll detail more in writing. Okay. You got anything you want to add to that, Becky?
Not really. I mean,
okay.
It's pretty much all there is to it.
Yeah. Okay, go.
Okay, Lagrange points.
Okay.
Basically, if you have two large gravitational bodies, like the sun and the earth, or the earth and the moon, or something like that, there are certain points where their gravity interacts such that there's points where it's really stable. Did I say 5? I thought I said 5.
There's 5. There's 5. The question says the Lagrange point, and there's actually 5 Lagrange points.
Yes, there are 5 Lagrange points. And let's see. I'm gonna try showing the picture for this.
Yeah, okay.
Wrong one. There we go. So there are 5 Lagrange points, and so this picture is of the Lagrange points for the Earth and the Sun. L1 is between, it's about 1 million miles away from the Earth, and it's between the Earth and the Sun, like directly between. And we have things that like to study the sun there. We have a couple of satellites. Solar and Heliospheric Observatory, otherwise called SOHO, and Deep Space Climate Observatory. So L2 is on the opposite side of the Earth. And things that really want to see far into the night sky, different observatories that are looking out into outer space, tend to be over there. It's really a good spot because it puts the Earth between the satellite and the sun, so it keeps it cooler. And then L3 we don't use for anything because we would never be able to communicate with it since it's always on the opposite side of the sun. And those 3 points are not stable.
Right.
But if you can stay right on the point, they are a good place to be. But basically, it's like, think about if you had like a marble on top of a hill. If you push it a little bit off, it'll just fly away. It'll roll all the way down. So they have to use their propulsion to make sure that they stay right in the Lagrange points. The L4 and L5 ones are about 60 degrees further along the orbit or further behind our orbit, the Earth's orbit. These are really stable Lagrange points. If you look at the orbit of Jupiter, there's a whole bunch of asteroids that just sort of group in these areas. Mm-hmm. So things are actually sort of attracted and they get sort of stuck there.
Trojans.
So what?
Trojans.
Yep. That's where the Trojan asteroids near Jupiter are. There's just a massive cloud of them. Earth only has one known Trojan asteroid. The rest of them are sort of around Jupiter mostly. So Lagrange points are just stable places that stuff kind of is in equilibrium. It's easy for them to stay right there. So that's pretty much Lagrange points in a nutshell. We tend to put our satellites in these areas because they, tend to stay, and it makes a really stable place to observe from. I can stop screen sharing so you don't just see Frank. So it's pretty simple. Do you have anything to add to those?
Why 5? How come there's not only 2 Lagrange points, or how come there's not a dozen Lagrange points?
Actually, it's just the way the gravitational interaction between the two are. There's just no other place where it happens to be stable. I don't have a better explanation for that. Do you have a better explanation for that?
Yeah, I would say more or less you get a 5th order polynomial. And so these are the roots of that polynomial, to say it simply. But yeah, it's the way when you work out the gravitational interaction, there happens to be 5 zeros, 5 crossing points. And that's why you get 5. So that's why there's not 2 and why there's not 10. So it just happens to be 5 for when you set the problem up. Okay, what else we got here? Where am I? Okay. Ooh, I'll take this one, but I'm sure you'll weigh in on this one. Talk about spectrometry. Is there an influence from the light emitted from a star and the light absorbed by the atmosphere of a planet? How can I tell where the absorption line came from? Right, so if you're far enough away and you're not resolving the difference between the star and the planet atmosphere, you're right, you're not going to be able to tell the difference. It'll all look like one object. So you have to be able to separate those two, either resolve it or somehow block out the light from the sun, so that you can put your spectrograph right on the purported planet and see if you can characterize the atmosphere. You want to say a bit about that, Becky?
The best way to do spectroscopy is for planets that move in front of their stars. The easiest way to do it, if you can't, just block out all the star's light, is to really, really, really carefully characterize the spectroscopy of the star, which lines it has from its absorption, and then when the planet moves in front, you try to analyze those subtle differences from light that moves through the atmosphere, and if you can see the sorry.
You. See, it's live. It really is live.
I'll just mute this for a second.
Okay, I'll take over. I'm going. Becky's off on call land. Let's see.
Okay.
So, yeah.
It stopped. And you can also, if you have a really, really good measurements, when this planet is moving to move behind the star, you can see the light that's reflected off the atmosphere, which you can tell some things about, and you can see the emission. But like he said, it's really very difficult to see the emission lines. They're much weaker than the absorption, and you have a star right next to it that's just a huge source of light. It's harder to tell the difference. So, and you can tell things from if you can measure it, what light the planet emits. you know, it absorbs then emits. You can learn something from that, but it doesn't necessarily relate exactly to what the star light is in. So,
right,
yeah.
you kind of expect the planet to emit mostly in the infrared, which is usually not what the star is peaking at.
That's why my research is with an infrared camera, because there's a lot of absorption and emission lines that are directly related to possible life, like possible signs of life in the infrared.
So what do you look for?
Right now, our filters aren't really working very well.
Yeah, okay, in principle.
Um,
what do you hope to pick up? Oxygen lines, molecular oxygen lines?
Oxygen lines would be ideal, because oxygen it doesn't exist freely in an atmosphere. The only way it can exist is if life is, well, the only way we know of that it can exist is if life is continually producing it. Like plants take in CO2 and then they release oxygen. It's the only way that free oxygen on this planet exists. We've never found another way to do it. Oxygen lines are very faint, so we have a harder time with those. So there's certain lines that you can look for that you know there's not going to be life. So it's what's called like a reducing atmosphere. If it's mostly just carbon dioxide, methane, things like that, it's highly unlikely that life can survive there, at least life as we know it. There's always been people saying, well, life might not be like us, but we can't look for that. We don't know what to look for. Unless we get a signal from an alien civilization, we won't know. All we can do is look for us.
It's absolutely true, but it doesn't tell you what to do.
Yeah, I mean, and also life, it appeared on this planet almost right after it became stable enough and cool enough for it to do so. So it seems like our type of life would be very easy to create, because it showed up really fast here. So those interactions must have been pretty quick and fairly common.
On the fair point, right, when Earth started, it did not have a oxidizing atmosphere, right? That oxygen came later with the great oxygen event. So life can get started without a huge amount of oxygen. So
yeah, it started without oxygen, but it tended to produce it after it started. So thankfully, otherwise we wouldn't be here.
Blue-green algae. Yeah, so just that's sort of where the state of the art is in astronomy. The raw discovery of exoplanets, that tidal wave, as far as research came, kind of has come and gone. I mean, we still search for them, but finding another exoplanet or another dozen exoplanets is not that exciting these days from a research perspective. There are exceptions to that, of course. If you find Earth's twin, that's really exciting. So there are cases where the discovery of one exoplanet might be news, but in general, the discovery of another dozen isn't going to make much difference. So really, where the state of the art is trying to characterize these exoplanets, and that's why sort of Becky does the research she does, because that's where the state of the art is trying to characterize what the atmospheres of these exoplanets are. So we've moved from raw discovery, adding another term in the Drake equation, where more or less the fraction of stars that have planets is pretty high. At least 0.6 at face value, and it wouldn't be surprising if they all did. And so, okay, so now we know planets are common, and now what is the characteristics of those planets? And so that's sort of where the state of the art is on that.
It's especially hard because the ones that, like, we don't say there's an exoplanet around a star unless it's been detected by at least 2 events have been detected. And so if you have planets around a star, they're like Jupiter and Saturn. They don't pass in front of their stars more than a few dozen, years. Most exoplanets that we find are moving really fast when they're close to their star, so they come around every few months. There's some I've measured that come through every day.
Yeah, we'll get more sensitive to masses that are farther out the longer we integrate, right? So we've barely been doing exoplanet searches for a dozen years or so, and so we wouldn't even pick up Jupiter or Saturn if they were around other stars. So you have to be doing this for, 20, 30 years in order to get that repeat event and be able to start being sensitive to Jupiter masses that are out, at 5 AU or something along those lines.
Although a big change now is there's satellites going up that are doing direct detections, and they're the opposite of the transiting exoplanets in that regard. The only ones that can see are the ones that have planets really, really far out, because otherwise they're too close to the star to differentiate their light. So we're learning how to do that, which is kind of cool.
It's actually the topic of one of the lab questions this week when you're trying to see if you could pick out Earth from the sun, just how different those reflection properties are. And so it gives you a sense of how bright the star is relative to the planet. So yeah, that was one of the lab questions this week. Okay, let's move on to another one. Let's see what we got. Any comments on Planet 9? What do you think about Planet 9?
We haven't detected it yet. The only reason we believe it exists is because we need to do very, very precise modeling of the Kuiper Belt objects, the big ones. They don't move the way you'd think. There's orbital resonances and tilts to their orbit that don't make sense. And so Planet 9, they expect, is probably 10 times or so the size of Earth. And it has such a long elliptical orbit that it would only go around every few thousand years. And the interesting thing is that they actually are talking about a possible Planet 10, which would be roughly the size of Mars and much closer. So depending on where it is in its orbit, that one would actually, despite being smaller, be easier to see. Because for all we know, Planet 9 is all the way out at the end of its orbit, which is really far away. So they haven't proven it because we haven't seen it yet. They're putting up new missions to try to find it, because we know roughly what the orbit should be. We just don't know where it is in it. So there's another possible Planet 10. And so far, nothing anybody's discovered disproves that they are there. But we still haven't found them yet, which is why they don't officially have names.
Yeah, I think we should just call it Planet 9.
I mean, it's going to take a really long, if we do find it, it'll be a really long time before people start using its real name. They'll just keep calling it Planet 9 because that's what we've called it for forever. Yeah. So they can't name it until it's found, because the person who finds it gets to name it. I mean, the name has to be approved by the international community, but they can put on what it's named. Which would be kind of cool, name something that is going to be around long after you're gone.
And just the interesting, so anyway, yeah, I'll just add a little bit to that. Yeah, the case is compelling. It's like shaking the box and it's got all the right rattles, but you haven't actually found it yet. But the case is compelling enough where people are putting resources into finding it. And just a little bit of the sociology of it is the people who have put this forward the most, Mike Brown and Bagatin. Mike Brown is certainly was one of the prime movers and advocate for killing Pluto as a planet. And so on the one hand, he's a Planet 9 Pluto killer, and on the other hand, he's a Planet 9 discoverer. So there's some interesting dynamic there on the human side of the game. So yeah, be excited. Stay tuned on that one.
And the other thing that makes it hard is, like, because it's so far away, they're not going to be very warm, so they're not going to be emitting much infrared radiation like the closer planets do. And there's so many other things out there. The Kuiper Belt objects are everywhere. So
yeah, it's not going to be easy to find it if it's there. So yeah, that hunt will continue. Let's see. You want to take one, Becky? Why don't you pick one?
Questions. Those are the ones that I
Okay.
I looked into, but I can, well.
I can just pick one and we can just blather about it a bit. Do we know where does the gravitational influence of the sun is 0?
Technically, the sun interacts gravitationally with the stars around it.
Yeah, technically the gravitational force is a long-range force. It goes out forever. So it's sort of the butterfly thing, right? So jiggle a distant star and it's felt here on Earth because gravity is a long-range force. So it gets very, very small the farther out you go, but it's never technically 0. Everything interacts gravitationally with everything else in the universe.
I think that they sort of say that it's not like the gravitational force isn't gone, but like when something is, or not Earth, sorry, the sun's solar system is when the gravitational influence of another star is stronger than it is of the sun. Gravitational influence isn't 0, but the sun's effect on something is less than the other stars around it.
There you go.
So it's like roughly halfway between us and Alpha Centauri is the end of our strongest influence.
So that would be about a radius of around 2 light years or something like that.
Yeah.
Right, where the sun is no longer the dominant gravitational influence. Other stars begin to dominate that influence. Right. Good. Okay. Cool. If there was an impact of an asteroid to the moon, large enough, will we see lava flux or will the moon just break into little pieces? You want to take a shot at that?
With a really, really large impact, you kind of, I mean, obviously it would depend on how big the impact was, but it's sort of like when, for example, we got hit way back before the moon formed, there was a lot of melted rock that got shot up into orbit around the Earth, and it collected and became the moon. At least that's the most popular theory. So if something really big hit, a lot of stuff would be shot off, but a lot of the stuff from the thing that hit would also break apart, and it would possibly just stick to the moon itself, which would be interesting considering the fact that the moon is in orbit around us at an equilibrium. So if it has a huge impact, what would happen to its orbit?
Yeah, we would know that. Yeah, and the other thing to remember is that anything coming in, that when that asteroid impacts, it deposits a lot of its energy in the thermal energy upon impact. And so the impact itself is capable of melting and vaporizing rock itself if it's large enough. So I think that's perhaps one aspect of the question. The other aspect, so are we going to see some sort of a lava flux? Yes. So I think the question is does that lava flux come from the heat of the impact itself, or are we somehow discovering that the moon has a liquid core? Probably a little bit of both. You're probably going to need a larger impact to sort of crack the egg, so to speak, to get to any molten interior that might be there.
We mostly figure there's not much. If there is something,
yeah, yeah. And then you have a really hard time distinguishing between what lava came from melting the rock because of the heat of the impact and what lava was there from the middle of the moon. That's going to be pretty tough to disentangle. But yeah, in general, if something hits, yeah, you're going to large enough, yeah, you're going to see some sort of molten rock, one way or the other. Where it comes from. But no, I don't think the moon just cracks into a bazillion pieces with nothing. That doesn't happen. No.
At the very least, whatever came off would probably gravitationally fall back on eventually.
Yeah.
Not within our lifetime, but it would eventually all coalesce again.
Right. And we'd have 2 moons. That would be kind of cool. Maybe we'd have 2 moons. What would Earth be like if it had 2 moons? I wonder what the influence of on Earth's axis would be, right? Because one of the reasons that we're around is because the moon did form. The moon acts as a great stabilizer of Earth's rotation axis. So unlike Mars, Mars kind of wobbles all over the place over time, which produces pretty large variations, which is not necessarily the greatest thing for life as we know it. We always have to say that, right? Life as we know it. So whenever we say that, that's kind of implied. But the moon is a great stabilizer, not only of Earth's axis, but it's also what drives the tides, right? So we've learned that. And so if you're trying to get life with nutrients going in and waste products going out, having a steady rhythm of tides is a good thing for inducing life. So moon has been super important. So I wonder what it would be like if we had 2 moons. I wonder if that's even stable.
I feel like if it was far enough out, it would be okay.
It was far enough out, it would be. Then the 2 in the middle are sort of, you can treat it as 1, right? So then it becomes a 2-body problem again. But I imagine it's just like 3 stars, really. I mean, it's just 3 objects, and I don't think on long time scales 3 objects relatively close, unless they're in a very special orbit, is stable. So one of them is likely to be ejected on some time scale. But it'd be fun for a while.
Tidal forces would be nuts.
Yeah, they would be kind of wild. Absolutely.
Could probably, if they're close enough, cause like volcanic activity.
Yeah, yeah. Because you're going to be torquing it's rock tides. You're inducing rock, like EO, just like EO, right? You're inducing rock tides. So let's see, what else we got here?
One is about an Uranus's magnetic field. And it is, the question is, could it be plausible that during the theoretical collision that tilted the axis of Uranus, the core continued spinning at a different angle due to angular momentum? And yeah, that's possible. Angular momentum would try to hold it in place. Don't know if that's the exact reason that happened, but it's possible. All depends on whether the axis of, like, what caused it to start spinning in a specific direction to begin with. So.
Looks like we got a new question there at the end. Where is the focal point of L2? So why don't you bring your picture back on Lagrange points? L2 is opposite the Earth. And I think you mentioned that L1 is of order 1,000,000 kilometers toward the sun?
They're roughly, both are roughly 1,000,000 kilometers in either direction.
Right, by symmetry.
Yeah, so the L2 is about 1,000,000 miles directly on the other side of the Earth from the sun.
At the level of this talk, we're not distinguishing between kilometers and miles. Okay, it's a factor of 1.6, so it's all okay. Okay, cool.
Yep.
At least I think that's what the question is asking.
I think so. Yep.
Okay. Unless somebody asked something, I think.
There was a question about the cores of gas giants.
Really?
If they have rocky centers beneath the liquid metallic hydrogen, how is it that there's no solid surface anywhere?
Right. I think people are either I'm not speaking clearly, that's always an option, or perhaps a misinterpretation of what is said. When we say no solid surface, we mean no solid surface at the outside. They're gas giants. Okay, so at their outer layers, where the clouds are, there's no solid surface below that. That isn't to say that they don't have any solid anywhere, right? So if you've got a rocky core, then way down deep, then yes, there is a solid surface. But typically when we say the gas giants, when we mean the solid surface, we're meaning the outer layers of the planet. So yes, it has a solid surface. If you go way down to the core, yes. But typically when we talk about the gas giants, there's no solid surface in the outer layers, like a terrestrial planet. So So if I'm being unclear about that, apologies.
Basically, also, if you look at it this way, it's the reason why we talk about the planet's outer layers being just gaseous is because the vast majority of the mass of the planet is the gas part of the atmosphere.
There you go.
So that's what we consider the planet, because the vast majority of the planet is just the gases.
Right. Also the radii, right? The radii are huge, and it's gaseous for, you know, 1,000,000 times more than the small, perhaps rocky core, ice rocky core at the middle. So yeah, by volume, by mass, by radius, they're gas. But they do have a little bit of a rocky core there in the middle. So, let's see. So I'm taking a look at Science Daily here. Let's see what news there might be if you want to cover a little bit of that on a couple stories. There's one. Moon has a water-rich interior. Really?
We can talk about the eclipse that's coming up.
Ooh, the eclipse. Let's talk about the eclipse and the Perseids. Okay, why don't you talk about the eclipse?
So it's August 21st, 2017. We're having a total solar eclipse, which means the moon is going to move directly in front of the sun.
Where are you going to be for it?
What?
Where are you going to be for it?
I think I'm going to be in Arizona for it.
Okay.
So the one thing that's different, that's odd about the solar eclipse is that you can't see it from everywhere on the planet, and there's actually only a very narrow strip of land where somebody's going to see the total solar eclipse. Hang on, they have a really nifty map. If I screen share
it. You had it up there in the beginning.
Here we go. So you will be able to see, if you are in the United States or even in Canada and Mexico, you will be able to see some portion of the solar eclipse. But the only place where it's going to be a completely total solar eclipse is if you're somewhere along this line, which is only about, I think, 70 miles across.
Yeah, it's pretty thin.
So in this tiny area right here, somewhere in the United States, is the only place that's going to be a total solar eclipse. But if you are, for example, in Arizona, it'll be, you know, between 70 and 80% of a coverage. So it all depends on where you are. I know a lot of people who are traveling all over the place just to be in that little strip right here.
Yeah, for example, I've got the American Astronomical Society, one of their divisions, actually two of their divisions, solar division and the high energy division are both having their meetings on that day, and I will be in Sun Valley, Idaho, which is right on center line there. If you bring your map up, there's your map. If I be quiet, the map will show up. And so, yeah, I'm expecting to get about 2 minutes of totality in Sun Valley. That would be interesting. How many eclipses have you made? Total solar eclipses have you seen, Becky? Just out of curiosity.
Not many, honestly. I'm never in the right place. Like for a while, you know, there were a lot of solar eclipses that weren't happening within the continental U.S. and I wasn't outside of it at the time. Total solar eclipses, I believe they only happen every 18 months or so. Yeah,
there's the Saros cycle. It would seem a little longer, but yeah.
So there's only been, you know, a few dozen in my lifetime. Not even a few dozen. Maybe like 20-ish.
I want to be on one of those planes where they fly. NASA will fly a plane to stay in solar eclipse for as long as possible. I think that would be a great deal of fun. But yeah, I think I've seen 3 in my lifetime. So this will be number 4. They're cool.
If you are in the US and you do want to look at it, you either need to use like the pinhole cameras, which I know some of you have already built, or solar eclipse glasses, solar glasses specifically. Sunglasses aren't nearly enough. And you need to be careful when you go on Amazon. Several of the companies that are selling those glasses, they actually don't meet standards safety standards. So make sure that you do some research. I think there's actually another link that they list like 4 companies that meet the current standards for safety for looking at the sun. So they're pretty cool. They're polarized in a specific way to filter out a lot of the harmful radiation. So.
Yeah, it might be dark, but there's still enough radiation to touch your eyeballs. So don't do that. Don't be that guy.
There's also an interesting thing that it's possible that we're not quite correct about the size of the sun. It wouldn't be much of a change, but they're going to, during the solar eclipse, do some measurements to see if perhaps the sun is just a bit bigger than we thought. It's just, very, very difficult to hold up, it's harder than just holding up a ruler and looking at it. The solar observatories have resolution of, like maybe 90 miles or so per pixel. So it's not precise enough to get a good calculation. So they're doing some research to see if that's going to be different. I don't know if they think that it might be different because of computer simulations they've been doing of eclipses, but.
So that would be the radius is defined by the photosphere, right?
I believe so, yes.
The optical photosphere.
Yeah.
Okay.
But the difference wouldn't be by much, like maybe a couple hundred kilometers at most.
Oh, right. Yeah. But
considering the size of the Earth or size of the sun, that's tiny.
Right. But it gets into the question somebody would want. How do you measure this? What do you mean by the radius of a gas giant? Where's the surface where you're measuring from? And so on the gas giants, it's traditionally taken to be an atmosphere pressure of 1 bar is where we define the radius of a gas giant to be. And it's kind of the same thing for the sun. It's a continuous body. So how do you define a radius of a gas giant? And so the typical radius that you will see quoted is the radius at which the optical light leaves the sun. So that's called the photosphere. And so that's a measure of the radius, the size of the sun. But the sun doesn't, of course, have a definite boundary. It's a continuous distribution of matter. But you have to have some way of characterizing what its size is, and so where the optical light leaves is a convenient way to do that. Perseids are coming up in August, so that's, what are we now? We're July 27th, so about 2 weeks. We go through the tail of Comet Swift-Tuttle. It's going to peak around August 12th, August 13th, I believe. Should be, if you're in a good dark skies, it should be pretty good this year. They're a little hard to predict, but well worth checking out. So if you start seeing things fly around in the atmosphere, you see bolides light up, it's because we're going through the annual Perseid meteor shower. So if you get a chance, go outside, check it out, lay down, relax, and see how many you can count in a dark spot. Even doesn't have to be dark, because if they come in the atmosphere, they're going to light up. So it'll be pretty cool. So we got 2. We got a solar eclipse and the Perseids coming up.
What's the date for the Perseids?
Perseids, well, it's the peak. The peak is August 12th, 13th, but again, it's a continuous distribution of stuff. So I believe, you could even probably go outside now. It's typically about a month, 5 weeks, so probably July 17th maybe to late August. You'll be able to tell that there's a bit more meteors in the sky, but peaking August 12th, 13th.
There's a new question on the discussion board about TESS. It's a transiting exoplanets survey, and whether it's going to rely on Kepler data. Kepler was specific in that it looked at only one region of the sky, always. So that was why it was able to measure planets that only went around maybe like once or twice like a year. TESS is not going to depend on that. It's going to do a full sky survey. So it's going to be looking for exoplanets that move around their star fairly quickly, because it's only going to spend, I think, about 30 days on each region of the sky. But unlike Kepler, it's going to map the entire sky. Depending on its mission length, it might do it more than once, which might let it catch more transits. But overall, only a small region of what it looks at will be what Kepler looked at. So it's more interested in looking at the entire sky. It's possible that when it looks where Kepler was, it might find something, but Kepler's long observation of just one place is very, very thorough, whereas TESS would only look at that place for a short period of time. It's unlikely it'll find something Kepler didn't. So.
Yeah, how many gyros, redundant gyros, will TESS have? I believe that TESS is scheduled for 4, if I remember right. Let's see. I can quickly find. Yeah, Kepler had 4, and 2 of them went kaput, and that's what made for the pointing. I don't actually know how many tests is scheduled, but certainly the lessons of Kepler are not going to be lost on anyone. So they'll put in as much redundancy as cost will allow within the mission spectrum scope. So I would expect at least 4, and maybe the reliability of them has gotten better since Kepler went up.
Yeah, Kepler was a bit of an anomaly. You know, usually NASA tends to use old, highly well-tested technologies, and having 2 fail on one satellite was really weird.
Pretty weird.
So.
Almost like doing a Google search and having nothing come up. Oh, let's see what I can quickly find.
Yeah, I can't find a specific.
I don't find anything specific on TESS. I don't know. Okay. Question there at the bottom, Becky, will JWSP help your research? And I think what the poster means is JWST.
Yeah, I figured.
So JWST stands for what?
James Webb Telescope.
Okay.
James Webb Telescope is going to be the next Hubble. It's going to study a huge variety of things, some of which is going to be exoplanets. It has an infrared camera that's going to be able to look for transiting exoplanets and to study them very, very, very well. But because it's so big and looking at so many things, people are going to be proposing for all sorts of stuff. Something like what I do would be to, if JWST finds something, small telescopes like the one I'm working on will follow up the information. So if they find stuff, which could be, it could potentially be very helpful for our research, we can follow up and confirm their results. Same thing with TESS. If it sees something, smaller telescopes will follow up the information that it discovers. So yeah, it can be very helpful. Large satellite missions can provide a lot of data, and then smaller ones confirm. It's like Kepler. Anything Kepler discovered, another mission had to confirm before they said, oh, yep, this is definitely a transiting exoplanet.
Right. Yeah, confirmation is huge, almost across astronomy. Detection is one thing, that's fine, but you got to follow it up to make sure, and usually to characterize it better. So it's usually up to the big scopes to detect a possibility, and then a whole slew of smaller scopes will come in and confirm, deny, characterize.
Because a good number of Kepler candidates were actually odd-shaped binary stars or false positives for a variety of reasons.
Yeah.
So they have to be confirmed.
Yeah. JWST will even potentially
It's going to advance a lot of people's research.
help mine a little bit. In fact, I have a piece of work in progress with Roger Windhorst right now, Becky. Going to be trying to use JWST to observe the first stars in the universe through gravitational lensing. And so in order to make that real, they needed modern models of what massive stars look like. And so I provided those. And other collaborators provided what those would look like through gravitational lensing. So we're hoping to submit this paper, I don't know, a couple weeks. So yeah, JWST is going to impact a lot of people's work, even if they're goofy theorists like myself.
That's the big thing about theories. It's the same thing as like the big telescopes discovering something. It has to be confirmed by somebody.
Exactly. I do like my theory to lie close to the data. So, so yeah. But the thing about theory is your case has to be compelling enough that somebody will spend the time, energy, and money to go look for it. Because you can create all kinds of stuff that nobody's ever going to spend the time looking for. So you want to make it compelling enough that people will go for it. Okay.
I think we got all the questions.
I think we got all the questions.
Something about white holes.
Oh yeah. A little off topic for the course, but okay.
Yeah, a white hole would be something that emitted light. If there's something that emits light, it's not going to be nearly as big as a black hole. And honestly, you could call that a star. Emitting light in all frequencies.
Okay, I hadn't heard that one before. That was pretty good.
I've never heard of white holes.
Other than the canonical star.
I mean, it's kind of what it is. It's a large gravitational pull that emits light.
Yeah, fair enough. Fair enough. That's what a star is.
Anything as massive as a black hole isn't going to emit light, except for some X-rays.
Yeah, right, this stuff goes down the drain. Traditionally, though, a white hole is sort of the anti-black hole. And so that's a point in space where a whole bunch of matter and light is just spewing out into the universe. And we've never, ever seen a white hole in that version of it, right? So yes, stars, you could take that point of view, right? Stars put out light, I get it. But it's not traditionally what people have meant by the term.
Yeah.
So, yeah, it's a theoretical possibility, but no one has ever observed one. And at least in modern research, I don't know anybody putting the time and effort into actually finding one.
They're just kind of, what would cause one? That's kind of the question.
Well, yeah, it's sort of the, well, if it goes down a black hole, where does it go? It must pop out somewhere else.
Oh, okay. That makes sense.
Right. So you can think of it as a tube, right? It's a tube connected through a gravitational singularity. So stuff goes in one end and comes out the other end in some sort of a conservation of mass thought. So it's a symmetry argument. If it goes in one place, it's got to come out another.
You would have a very difficult time detecting that unless a whole lot of matter went into the black hole at once.
And a whole bunch of stuff is coming out of a white hole. Nobody's ever seen one. Personally, I doubt anyone ever will. I think once it goes down the hole, that's that. So yeah. So yes, it's one of those things that in theory exists. It's a mathematical possibility, but no one's ever seen one. So there we go on that. All right, one more sweep, see if anybody's posted anything new. Otherwise, I think we'll end this one. We're coming up on the hour. Oh, we got one new question. Just a thanks. So on that, yeah, we'll take that. Thank you. You're welcome for all your multitude of questions. They're Rocky Antansky Max. I assume Max is the first name. So thank you for asking your questions. At least I had fun for this last hour chatting about planetary stuff. So at that, I think we'll sign off. Thank you very much. Ask any questions that you have on the discussion board, either as a follow-up to this YouTube live session. Or of course, we're also coming up on the end of the course. So if you have any questions on the lab, I believe next week is going to be the final exam. So if you have any questions on any of that, post away on the discussion board. All right. Thank you, everyone. Bye-bye.